Let's talk about orthogonal sets. So a collection of vectors v1 up to vp in Rn is called an orthogonal set if the pairwise dot product, so vi dot vj, is 0 for all I not equal to j. And so notice the dot product is commutative, so vi dot vj is equal to vj dot vi, and so we only actually need to check one from each pair. So for example, if I wanted to show that a set of vectors v1, v2, and v3 is orthogonal, I really only have to check three things. v1.v2, check that that's 0, v1.v3, check that that's 0, and v2.v3, and check that that's 0. So let's take a look at a concrete example. Let's see, is this set -1, 4, -3, 5, 2, 1, 3, -4, -7, is it orthogonal? So I compute the dot product of the first one and the second one, and I get -5 plus 8 minus 3 equals 0. Good. I compute the dot product of the first and the third, and I get -3 minus 16 plus 21, which is not 0. So as soon as I notice that, I can say that no, this set is not orthogonal. Right? It's only orthogonal if all the pairwise dot products, vi dot vj, for I not equal to j, if all of them are 0. Okay. An orthogonal basis is a special kind of basis for a subspace. It's a basis that's additionally an orthogonal set. And these things are very nice, right? So an orthogonal basis is nice in the sense that it's easy to compute the coordinate vectors if you're using an orthogonal basis. And so it's easy to express vectors in terms of an orthogonal basis. So take a look at this theorem. Suppose u1 up to up is an orthogonal basis for a subspace W. For any vector y in W, well, we can express y as a linear combination of u1 up to up. That's because u1 up to up is a basis. But the additional bang for your buck that you get, because you know that this basis is orthogonal, is you get an expression for each of the weights. So Cj is just y dot uj divided by uj dot uj. This is true for j from 1 up to p. Right? So you don't actually have to solve a linear system in order to express y as a linear combination of u1 up to up. So that's what's nice about this orthogonal basis, is it's easy to express vectors in terms of an orthogonal basis. So let's take a look at a concrete example. Consider this basis B, which is the vector 2, -3, and 6, 4. Here's an orthogonal basis for R2. And let's try to express the vector x, which is 9, -7, as a linear combination of u1 and u2. Well, u1 and u2 is a basis, and so I can write x as cu1 plus cu2, and the previous theorem just tells us how to compute c1 and c2. c1 is x dot u1 divided by u1 dot u1, and so that is 18, which is this 9 times 2, plus the -7 times -3, which is a 21, divided by u1 dot u1. So that's 2 squared plus 3 plus -3 squared, so 4 plus 9. That's a 39 over 13, which is 3. So it tells us C1 is 3. Similarly, I can compute C2, which is x dot u1. So that's the 6 times 9, which is 54, plus the 4 times -7, which is a -28, divided by 6 squared, which is 36, plus 4 squared, which is 16. So I get 26 over 52, which is 1/2. And so that tells me that x is 3 times u1 plus 1/2 times u2. In other words, the b coordinate vector of x is 3, 1/2. And so notice that's an easier computation than row reducing. Let's next talk about orthogonal projection onto a line. So consider this line L going through the origin and this vector y sitting in R2. And I want to talk about and compute the orthogonal projection onto that line L. And so what is it? Well, it's this vector y hat, or it's also denoted proj L of y. It's going to be a vector on L, and it's the closest point on L to y. Right? If you sort of drop a perpendicular from y onto L. And there's a formula for computing it. It's given as a scalar multiple of a vector u, where u is any non-zero vector in L in the line. And the coefficient that you need, the scaling that you need, is y dot u divided by u dot u. Okay? So the projection is the closest point on L to y, so I mentioned that, because this from y to the line L is just this perpendicular line, and that's the shortest distance you can get. And so the length of y minus the projection is the distance from y to L. Right? So this gives you a way to compute how close does y get, or how close is y to this line L. You just compute the length of y minus the projection. So let's take a look at what this says. Well, we can decompose y as the sum, the projection onto L of y, plus this orthogonal part, this y minus the projection. And so this first piece is in L, and the second piece is in L perp. Right? And so we've decomposed this vector y in R2 into some portion that's in the line and some portion that's perpendicular to the line. Right, so that's the piece, that's the projection that's in the line. The portion that's in the part perpendicular to the line is shaded here in orange, and if I want to add, I just shift that up and see that they add up to y. All right, let's take a look at an example in detail. So suppose I have y, which is this vector 3, 1, and L is the line through the origin that goes through the vector u, which is 8, 6. Now the projection onto L of y, I can just use the formula. It's this multiple of u given by y dot u, which is 24 plus 6, divided by u dot u, which is 64 plus 36, times the vector u. And so I can simplify that and just compute. That's 30 1/100ths times u, or 3/10 times this vector 8, 6. And so that's just 2.4, 1.8. And so then y minus this projection is just the vector 3, 1 minus 2.4, 1.8. And I get this 0.6, 0.8. And so I can decompose y as 2.4, 1.8 plus 0.6, 0.8. And so that's the decomposition into a portion in L and the portion in L perp. The 2.4, 1.8 is the point in L that's closest to y. And if I compute the length of the part that's perpendicular, so that's the length of this vector 0.6, 0.8, I get 1, which tells me that the closest the line goes to the point y is distance 1 away.